Welcome to Introduction to Electricity. What we're going to do is we're going to use water flow as an analogy. Okay, that's a helpful kind of image or example that we can use to help us understand the flow of electricity. Now, in order for us to go on with this analogy, let's talk a little bit about water flow. So when you have equal water pressure, that equals no flow. Since it's equal, there's no water going into one tank or another. So if you have unequal water pressure, that means that there is going to be flow. Flow to equilibrium. So what's going to happen is the water is going to go down to a point, which is here. It's going to flow into here, and this tank water is going to be raised until they're equal. And we know that equal water pressure equals no flow, so that means it's going to stop. Moving back to the actual electricity, these guys right here, they are symbols, schematic symbols, that help us to draw circuits very simply. So this right here is a resistor, and this is something in a circuit that does work. So in water, this will be something like a turbine. The water will move this turbine, will cause it to turn and maybe produce electricity. In a circuit, this is something like a light bulb. And this right here is the symbol for a battery of cells. There are actually two cells here, and they're connected. So there's one cell, and there's another cell. So the battery of cells is a power source. So electricity is simply the movement of electrons. So we're going to use the movement of water as an analogy for the movement of electrons. So let's look at this one. In each example, which will create less resistance in our water diagram and in our circuit diagram. So here's two tanks attached with a pipe. Well, in the water diagram, to create less resistance for the water to flow into the other tank, I would say that we would have bigger hollow pipes. In the circuit diagram, that would translate into bigger wires. So take a look at your cord that charges your phone. Take a look at the cord that charges the laptop cart. There's a bit of a difference in diameter there, and that's because there's way more power required to, charge 30 laptops than one phone. Also, the material. For the water diagram, the pipes can't be absorbent. Something like metal or plastic would be best. In the circuit diagram, what's going to create less resistance is also material. But we need to have conductive material. There's no such thing as plastic wires. So copper. Copper is has very little resistance. Sometimes it's in our best interest to have a little bit of resistance, like for tungsten. Tungsten has very high resistance, but you need that in the filament. Sorry, does that look like a light bulb to you? It's not that bad. The tungsten is actually in these filaments here. The reason why it's very high resistance there, it means that the electrons move very slowly. But that's what produces actually the glowing in the light bulb. And just to be clear here, in an electrical circuit, resistance is measured in ohms. And then we've got that Lululemon symbol here. That's hip with you kids, right? So what change in the water diagram will create more water pressure? We here are now going to talk about the difference in potential energy. Well, if I would take this tank and extend the tank all the way up here, I would say that a water molecule that is up here, fill this with water, a water molecule that is up here has way more potential to do way more work than, say, a water molecule down here. So, the difference in height, so delta, the difference, that's just a physics symbol for difference. The difference in height, or the change in height, equals water pressure. That is our potential energy, difference in potential energy. Now, the job of a battery is to raise the energy level of the electrons. It's to raise from a very low energy to a very high energy, and that difference in energy level, that's our potential difference. Okay, that's our difference in potential energy. So if I were to look at this schematic right here, electrons flow from the negative and they go around the circuit, they go through the resistor, they use up their energy, and they enter back into the battery. Well, the electrons leave with high energy, and the electrons enter back into the positive side of the battery at low energy. So electrons have a low energy level because they used up all their energy in this resistor, whether it be a light bulb or some other thing that does work. And the difference here from the high to the low, that is our difference in potential energy. So for example, if I have a 9-volt battery here, I have my positive terminal and my negative terminal. And what I'm going to do is electrons are going to flow out. They're going to do some work. Here's a light bulb. They're going to flow back in. So literally what happens is electrons flow out at a high energy level, do all their work, and their energy level is lessened. They go back to the positive, and it's the job of the battery to power them up. So they go from 0 volts, they get raised to a power level of 9 volts, and then they exit again. Just to make this official, even though I used the units already, potential difference in energy is measured in volts. The third thing that we want to talk about is the current. Now in a water diagram, that's how much water is flowing. And how can we measure it? It's a rate of flow. When we say rate, we think ratio. So if I were to have a hose, and I were to have a river, this is not to scale. Look at my beautiful art. I would say that the current in the hose is much less than the current in the river because the river is much bigger. So river has a higher current, because you take some amount of water and you divide it by time. So this right here is the amount of water. The amount of water per unit of time, whether it be seconds, minutes, hours. Now here in an electrical circuit, the current is how much charge is moving at a particular point. And when we say charge, we're saying negative charge because it's the movement of electrons. Now in an electrical circuit, the rate of flow of electrons is measured in amps, which works out to approximately 1 coulomb, which is 6.242 times 10 to the 18 negative charges per second. Sometimes when it's in scientific notation like that, it's really hard to appreciate how huge this number is, but let's do it on the calculator. 6.242 times 10 to the power of 18. Whoa! That means 6.2420000000000000000 negative charges per second, people! Per second! That's huge. So, the three things that we talked about were resistance, and then we talked about potential energy, and then we talked about current. So let's make a formula for the relationships between these things. Thank you, scientific community, for using I for current. That's not super intuitive, but resistance is more R. And we're going to let V be our potential energy, which makes sense because it's in volts. So as resistance goes down, the current goes up. So when we think about our first one, all the way up here, we said as the resistance goes down, as the pipes are bigger, it's easier for the water to flow. So as resistance goes up, as resistance goes down, the current goes up, or we can say as the resistance goes up, the current goes down. This is called an inverse relationship. As potential energy goes up, okay, as the height of the water in the tank gets higher and higher and higher, the current, the flow, goes up as well. So as I would say, as volts go up, the current goes up. This is an example of a direct relationship. So if I were to create a formula here, I would say that I would pick what's common to both. So we talked about the current being common to both. So I equals something over something. So the inverse relationship is with the resistance. So resistance goes in the denominator, and the potential difference goes in the numerator because it's on the same level. As the volts go up, the current goes up, or the amps go up. We can rearrange this formula. So if we want to solve for resistance, we can say that that is V over I. Or if we want to solve for V, we can go I times R. One more thing before we summarize, I want to talk about the difference between series and parallel. So if I were to draw batteries or a battery of cells in series, I'm going negative end to positive end. They're in a line. Whereas with parallel, if I were to do parallel cells, I would put them one beside each other. So the way that this could actually look is you would have the positive ends like this, and positive ends like this, whereas this one would look more like this. If we wanted to, I'm just going to extend with this one. If we wanted to draw light bulbs in series, I would have them going along the same wire. So these two light bulbs are in series because they're going along in the same loop. Whereas if I were to draw light bulbs in parallel, each light bulb, each thing that's doing work, would have its own little pathway. So this is going to come up in a few of your labs, so I just wanted to make sure that you had a good understanding of it. So let's summarize here. Electricity. No, I always do that. Is the flowing of electrons. 3 important aspects are resistance, which is measured in ohms, potential difference, which is measured in volts, and the current, which is measured in amps. The formula that relates all three is I equals V over R. And if we want to solve for V or R, we can use the different forms that we identified up here. Happy building!